All right. So let's try to introduce some other concepts which are very useful and particularly for calculation. So what we plan to do right now to define clearly what random elements, random variable vectors are, and to describe some of their properties like distribution, densities, and then, of course, to look at some special cases like Gaussian, which is a very useful probability distribution, but also has some limitations. As you may know, no physical quantity. World is not Gaussian. Why I'm saying that. The property of anything, material properties, phenomena, are taking value on a bounded interval. So that tells you the story. Gauss distribution from minus infinity to infinity. Now, don't take it in an absolute terms. It doesn't mean that you have just to junk this distribution. No. As you know, all models are wrong, but some are useful. So it depends a lot of the setting in which you are using. For example, if you try to describe with a Gauss distribution material properties, and the average value of that material properties is very close to zero, and the variance is very large, obviously the Gauss distribution is wrong, because it's a very large probability you are going to see negative stiffness or something like that, which makes no sense. Right? But on the other hand, if the mean is large relative to the uncertainty, Gauss can be a very good distribution. And it's used extensively for convenience, of course, but one has to keep in mind all the time what I said before, that all models are wrong, but you can use them if you understand their limitations, and then it can be extremely useful. All right. So let's try to define right now what we mean by random elements and how to proceed with the description. So I'm going to use just an abstract concept just once, and after that it becomes very, very applied, so we can function with it or used in applications. So let me define first what's a measurable function. So if you consider a certain function x from a probability space, so we have the notations, I think you've seen them enough to remember what it is. Sample space, sigma field, probability measure. To, for example, the d-dimensional space is Euclidean space, right? With a structure on it. You remember Borel sigma field we introduced? So I'm going to write here what it is. So it's Borel sigma field on RD. So it's a sigma field generated by the intervals in RD. On the real line, an interval, you know what it is, right? In a higher dimensional space are rectangles, which can be open or not to the left. So such a function is measurable. If the following thing is true. Okay. So I'm going to go slowly like this, with this one just to make sure that we grab the physical content of it. B it's a Borel set that is in this Borel sigma field. So x is the inverse of x. What does it mean? Let's make sure that, I'm sure you know it, but let me write it anyway. To consist of all the elements of omega which are mapped by x in this subset B. Yeah, this, don't think probability. This is a definition of any inverse function. Don't think probability at all right now. It's just a function. Right? If you take the inverse of a function, this is how it's defined. So what do I say? It's measurable if this it's an event that is in F for all B Borel. So you are seeing right away why it's absolutely necessary to have this condition, because otherwise I cannot define the probability on this. If this is an event, then probability is defined on it. Okay? So the second definition and then things are going to come that will be much more familiar to you. And, you know, these somewhat abstract concepts are really necessary to be able to go beyond just using some numbers without getting to the bottom of it in order to solve difficult problem in stochastic mechanics or in physics problems. So the second definition is a distribution of x induced by p. And we know p is a probability measure, right? Is the following. F of b, b, it's any Borel set. And just bear with me for one more minute, and then we get on ground which is much more familiar to you. So this is called the I already wrote. Distribution of x induced by is the following. Now, the definition is meaningful. Why I'm saying that? Because by construction, this is an event. It's a member of the sigma field. And the probability is defined on F. So that's a correct definition. Okay? So this is it. That's the distribution of this random element. So let me repeat this to definition one more time, and then we apply them directly and go to a ground on which you are quite familiar. So we first define a measurable function. So to do that, we have two items. This probability space and the outcome. In this case, I define it in this set in RD, but you can define it also on space of function in which you obtain random processes and so forth. But for our objective at this time, this is a Euclidean space with a corresponding Borel. And we say that the function is measurable if it satisfies this condition. Since the function is measurable, I can define its distribution because by definition of measurability, this is an event. Okay? So we're good with that? So now I'm going to consider a special case. Special cases. D is equal to 1. That is, the outcome of x, it's on the real line. And remember what the Borel sigma field is. It's generated by intervals. So we take d equal to 1 and take d to be this, where x is a real number. Right? All right. So then I'm going to define the distribution. Right? So the distribution of x in this setting I just copy the definition for this special case is a probability from there, right? Can I write it this way? This is uppercase, this is lowercase. Right? This is simply this x minus 1 for this b I have considered. Yeah, does it work? And how we usually denote this, instead of having this fancy notation, what we simply call it? Our notation is simply f of x. And we call it cumulative distribution function or just distribution function of x. Okay, so this is our familiar CDF. Right? So the entire distribution of this density comes from the probability structure you induced originally. So that becomes very important, this type of concept, when you really go to solve very complicated stochastic differential equation with the coefficient, random functions and all these things. You need to go to these roots in order to be able to solve the problem. I'm sure some of you are familiar with numerical methods, deterministic method to solve differential equations. You have to discretize the physical space. Whether you do finite element, finite differences, doesn't matter. Well, you have to do something similar in the probability space when you do numbers. You cannot do numbers on uncountable problems. You have to discretize. And the discretization of this complex function of time and space comes from that place. This is what you have to understand. And we are going to touch on this matter later on when I talk of stochastic differential equation, in which since there are so many things, I think I'm going to give a slide presentation and stop at different places to help with understanding. All right, another special case, d strictly larger than 1, and you know right now where I'm heading, right? So the same thing, we are going to have distribution of x induced by p. And the event I'm going to consider, B, it's a product of rectangles, or on the real line. That is, it's I 1 to D minus infinity to xi. So if you want a picture for this is a rectangle I'm talking about. x1, x2. In 2 dimensions, that would be the rectangle. Everybody can see that? Yeah? And then the distribution. It's again the same type of formula. I think I can simply write it in this form. That the coordinate xi is smaller than the little xi. And this is true for all the coordinates. And our standard notation for this It's f of x1 up to xd. And we call it perhaps joint CDF. Okay? But this is a sequence. This is how you get to describe the distribution of random variables and vectors. Incidentally, of course, is D1. We usually call it random variable. If this is strictly larger than 1, we call it random vector. Everybody could guess these names, right? Random because we are in the random world, vector and not because we are. And two important concepts related to these things. The derivative of this quantity, provided it exists, is called density. And the derivative is called joint density. That is from here. Is a PDF. And from here is a joint PDF. All these partials, right? So that would be the joint PDF. Now, distribution density provides full characterization of random variable vectors. If you know this, you know everything. Okay? So, let me give you some example, or before the example to expectation. So now we are going to set in this framework, which you are very familiar with. Okay. Expectation operator. So let's X be a random vector. So you can refer to it as an RD valued random variable. And as we discussed, this random element is completely described by either a joint CDF or joint PDF. And consider a function and just for simplicity, suppose it's continuous. Because it's continuous, measurable, and we don't have any other type of problems. And we are interested in this quantity. And I'm sure you dealt with, some of you at least dealt with this quantity in reliability studies. G, for example, can be defined a safe set if it's smaller or larger than something. And we are interested in calculating this so-called expected value of this function. G of x, it's a real function, right? By definition. And now, how we get to this formula is not a big deal, but it will take me like 10, 15 minutes to prove it, and let's accept it for the time being. By intuition, if you fix x, the probability of this x is roughly described by this increment of the CDF. Or if you don't like it in this form, you can write it in this form. Yeah. So that's a way to calculate it. So basically what I'm going to weight the value of g at a particular x with this probability f x dx. Add all the contribution, and of course you find the average value. The expectation, it's exactly like arithmetic expectation, just is loaded a little bit. Instead of putting, when I give you three numbers, say what's the average, you say 1 plus 3, it's divided by 3, it's equal to something, right? which is equivalent to say that I weight 1 by a third, I weight 2 by a third, and so forth. Here the weight depends on how much you believe in that particular weight. Okay? But conceptually the same thing. Now, expectation has two important properties. One, it's linear. No surprises. It's an integral. Integral, it's linear, right? Which in very simple terms means the following. If you do the expectation of the sum of two random quantities, so expectation of the sum is the sum of expectation. Okay. And one more thing. The expectation of the product of two random quantities. If x and y are independent, and I don't think I define it, so I'm going to define it right away. So x, y are independent. So, of course, there are much more, many other properties, but for our purposes, in this lecture, this is what we need to remember. Linear and expectation of independent, product of independence, product of expectation. And in terms of independence, so x and y random variables are independent if the joint density, and I'm indicating this by this, so this is a joint density of x and y, is a product of the densities. Now, the proof of this is not trivial. The proof has to strive for independent on the probability space. It's not trivial, so you just have to accept it at this time for this level. It involves some theorems which, they're not directly proof. But this is what we are going to operate, and I'm sure you operate it with as a definition. Now, given that x and y, can we prove this very quickly? Yeah, it's obvious, right? You write the definition, the density splits into, the integral are going to split into integral, done, right? Okay. All right. So now I think we're ready for some one other things, so-called second moment properties. And some of you who have done are familiar with so-called form, ZORM tools of reliability analysis. I'm sure you dealt quite a bit with this type of properties. Of random vectors. So we are going to be in the same setting, that is x, it's a RD valued random vector. And we defined the first two moments of this random vector. This would mean second moment properties. So it's a mean vector. And when I'm writing these things, I assume that these first two moments exist. Not all random variables have first two moments. May not exist. For example, the Cauchy. Have you seen the Cauchy distribution, right? Of course, doesn't have even the mean. So mu, this is a vector, is the expectation of x, and is simply the expectation of each component of the vector. That is, mu1 is the expectation of first component, and so on. Mu, I said d dimension, right, is the expectation of the last component. Usually we look at them as a column vector, and that I put the transpose. Correlation matrix. Let's call it R. And it's the following matrix. Rij is the expectation of the product. I and j are running from 1 to d. And the covariance matrix let's call it gamma. It's a similar expectation of second order moment, but you pull the mean out. You center the moment. Right? So it looks like this. Okay. So these are the two moments. So you realize that the correlation and covariance metrics are equivalent information. If you open the parenthesis here, you are going to obtain the covariance is the function of correlation and the mean vectors. Right? So one or the other, it doesn't matter. You can obtain one from the other very easily. Well, one thing I like to mention these two matrices are positive definite. Okay? Or, some people instead of positive, they call it semi-positive definite. But I tell you what I mean by that. That is, we have the following. A being any d-dimensional vector, that if you consider this product, now first you realize you can multiply these matrices, right? This is, after I transpose this 1D, D, D, 1D, so you end up with a scalar. This is what I mean. The proof is very simple, and let me just give you a very quick one. Consider this quantity, where AI are the coordinates of vector A. This is a random quantity, random variable, right? Square it, still random variable. Expectation of it. Now, the expectation of a positive random variable is positive, irrespective of what AI is. But what I wrote here, it's exactly this quantity. Is it clear, or shall I write it explicitly? Yeah? I'm claiming that this is this. Okay, let me write this parenthesis explicitly. So this parenthesis square, I have a double sum, right? I, j, 1 to d, ai, aj, rij. Shall I write more, which is obvious? Shall I write it? Good, right? Okay. So this is a proof. It's right there. Okay. And finally, regarding with this, if you consider two components of this vector, xi is uncorrelated of xj, and of course I is not equal to j, because it's the same thing. It's not going to hold. If gamma ij is equal to 0. Right? Everybody's seen the definition, or most of you have seen it. Okay. So, question. Let's say xi and xj are random variables. Okay. Or let's call it simply to avoid all these indices. Okay. And we know the following. xi are independent. And xy are uncorrelated. Any relationship between the two? This is an important concept. Do you think it's true this way? That if x and y are independent, they are uncorrelated. You remember this formula? So that's true, right? What about backwards? Backwards is not true. Generally, it's not true. And you'll see right away I say generally. But to convince you that it's not true, I'm going to give you a counterexample, which is a very simple one. Do you have enough probability for today? I hope not, because still some's got to go, right? Okay. So counterexample. X, I know that I can use it, although I didn't define formally. That is, X is Gaussian with 0 mean and unit variance. And Y, x squared minus 1. Right? So, anybody can tell me what's this expectation of Y? So it's expectation of x squared, which is 1 minus 1. Shall I write 0 here? Right? The expectation of x squared, it's 1 because the mean is 0, right? So that's the variance. So we're good with that? So are they dependent or independent, x and y? Well, are obviously dependent. They are functionally dependent. If I tell you that x is 2, what's y? 3, right? So you know x, you know y. It's clear they are dependent. What about the correlation? Right? It's to be the expectation of x cubed minus the expectation of x. So I use here the fact that E, it's a linear operator. Now, we know that the expectation of x is 0. Expectation of x cubed is 0. Again, I didn't define it. I'm going to define Gaussian in a second. But you know, this is what the skewness as a distribution, which is 0. So what that's a very simple example showing you that uncorrelated random variables may not be independent. Okay? So keep this example in mind. So you are not going, it's very simple to remember, and you are not going to mix dependence with lack of correlation. Okay, Gaussian. So Gaussian vector X with mean mu and covariance matrix gamma, and usually we denote this by saying n, and if we're really very careful, put a this here to indicate that it's the dimensional vector. So that tells you the story about it, right? And the joint density of such a vector is the following. I think this is a half here. Let me look to make sure that I get it right. Okay. Okay, so you recognize in this formula, all I need to specify is the mean vector and covariance matrix. Right? Now, if you look at this Gaussian vector, if gamma, or if the components of X are uncorrelated, so let's note this. Xi are the components of X are uncorrelated. What does it mean if they are uncorrelated? How the covariance matrix look like? All the off-diagonal terms are 0, right? So gamma is a diagonal matrix. That is, all the off-diagonal terms are 0. So what's going to happen when you go here? The inverse of gamma, how is going to be? Also a diagonal matrix? So, for example, if gamma looks like this, sigma 1 square, sigma 2 square, sigma d square, the inverse of it would be 1 divided by sigma 1 square, 1 and so forth. So it's also diagonal. So what does it mean? This product here is going to become a sum of xi mu I minus mu I square divided by sigma 1 square. So exponential will become exponential of sum, which is a product of exponentials. Therefore, it becomes independent. So this is, when I wrote here, I said generally, because it's a major exception. It's a Gauss, and there are some other distributions which have these properties. So if they are uncorrelated, then are independent. Okay. One other property, so this is one thing. The other, well, let's put it a definition. Have you seen characteristic functions? Yeah? So that's an alternative way to characterize or to describe random vectors. characteristic function of x is usually denoted in this way, where u is an argument again in RD and is an expectation. U prime is transpose, right? So that's well defined because u prime times x, it's a real number, right? So the exponential, it's well defined. And if you want to write it explicitly, of course, can be written in this way. So you can see that density and characteristic function are Fourier pairs. You know one, you know the other one. So the characteristic function, it's an alternative way of defining completely a distribution, in particular Gaussian distribution. But the nice thing in Gauss, and this is, it has a very nice form. So for Gauss, has the following expression. So again, it's an expression. Please distinguish. This is mu. It's a mean vector. Gamma is a covariance matrix, and u is the argument. Now, homework for the afternoon, which is, I'm sure you are going to, maybe already you did it, but you can do it in very quickly. Show that the following random variable a, which is defined as, I use a, okay, a times x is Gauss if x is Gauss, where of course this is an RD vector, and A, it's a matrix which can be D prime D, right? So you can multiply it. So in other words, the output Y doesn't have to have the same dimension as the input X. And the hint is the following. Calculate the characteristic function of Y. And you find out that you end up with something like this, and you identify both the mean and the covariance matrix of Y. Okay? All right. So let's try to conclude the day with Monte Carlo simulation. Okay? It's a very useful tool and becomes much more used because computers are getting faster, of course. But don't think that Monte Carlo solves everything. And I'll give you an example. In some of the work I'm doing for Sandia, this is a national laboratory in the United States, and they are involved in massive computation. And a single run there on the supercomputer may last for days. So even with today computers, brute force Monte Carlo cannot be always used. When you go to real problems, you have to do some smart Monte Carlo. And I'm going to touch a little bit on this when you solve stochastic differential equation. But it's very useful too. So let me just illustrate the idea. I'm pretty sure you are familiar, but I want to do two things. to show how it's done, and then why it works. Okay? So let's try to do these things right now. So Monte Carlo simulation. So our setting is the following. X, it's an RD valued random variable. It doesn't have to be Gaussian, right? Random variable. And Y, it's an output. And just to write it simply, I'm going to assume that it's real valued. So it's a mapping of X. And I assume that it's real value. You remember we started our discussion this morning with such an output that was a displacement, the tip displacement of a cantilever, and depended on the two-dimensional random vector stiffness and load. That's a model, right? And our objective is to estimate the system reliability defined in this way, the probability that this output is smaller than the critical value. Sorry. Okay? By Monte Carlo simulation as indicated here. So is this clear what we are after? Think of X, as I said in the first example we have discussed, stiffness and load. Y, tip displacement of the cantilever. We wanted it to estimate what the probability is that tip displacement does not exceed a critical value, whatever that value is. Okay? So, algorithm is the following. Step 1, generate an independent samples, call them x1 or x1 xn of x. We are going to discuss later on how we produce this, such samples. Suppose we are able to do that. And if we do that and calculate the corresponding function, samples of the output. Guys, can you read this? Nobody's complaining, so if you don't complain, I assume that you can read it. True, correct assumption? Okay. Calculate the corresponding samples. Y1 up to Yd of Y. This is the output of interest. You know, you can have whatever output of interest, quantity of interest you have. So that's step 1. As I said, I own you this part. We are going to discuss how to produce sample for that. Step 2.
Sorry, that Yd is not necessarily equal to xn, no? So,
oh, all right. No, I just, it's that a typo. It's happened in the books too. Thank you very much. Yeah. All right. Step 2. Now I try to construct an estimate. Estimate this probability. Okay, estimate the reliability by, and I put a hat here on it to indicate that it's not a true value, it's just an estimate. Here, it's y critic. That is, it's exactly this, but I put a hat on the top of it because it's an estimate. It's not the true value. By the following. Okay, so let me make sure that we understand this formula. This is an indicator function. That is, if the sample is smaller than the critical value, I have a 1, if not 0. So, for example, if n is 100 and say 50 out of 100 yi's are smaller than y critics, the probability, our estimate is 50%. Right? So this is Monte Carlo. Now, why do you believe this? So this is a y. So why it works. And this is why. We have to think again in probability terms. And this is what the thinking is. Call yi independent copies of y. Y is the output, right? So these are independent copies of y. We defined y, we know what y is. And now we are going to construct an estimator. This is an estimator. Estimate, it's a number. The estimator, it's a random quantity. Okay? And construct the estimator and to distinguish of this, instead of lowercase p, I'm going to put uppercase p. Again with a hat. Same formula, lowercase going to the uppercase, and let me make some comments. What we try to accomplish by this approach? Since y is random, it's clearly this is a random variable, right? So any sample of this random variable, it's an estimate, right? If I draw samples of this yi, I'm going to have a formula exactly like this. If I draw another sample, I'm going to get a different number and a different number for the next samples and for. Well, we want to see what are the properties of this random quantity. So what to expect to have? We must require. Do you want, if the true probability, let's say, is 0.8, do you want the expected value of this random variable to be 0.1? That would be pretty bad. That would be a bias estimator. So you want to require at least that much. On average, this estimator, it's equal to the target value. And then you want something more. Okay, that's good, so it's unbiased, but you want something else. The spread about this true value is rather small. Okay? That is, even if you hit the expectations, the true value correctly, but the spread is like this, that is going to be a useless estimator, because when you calculate the value for a particular sample, this is a true value. You make it here or there, so you cannot trust it. Okay? So these are the two conditions which we have to impose. The mean, it's obtained right away, and the variance is not difficult, but take a few more lines. So everybody recognizes this is a random variable, right? So it's legitimate to calculate moments of it. Expectation, it's a linear operator, so I can go turn by turn. Okay? What's that expectation? It's exactly the true probability, the probability which I don't know. So what does it mean? That expectation is equal to, well, you add n times the same thing divided by n. So the estimator is not biased, it's unbiased. So that's good. So now I have to calculate the variance of it. So what would like the variance to do? Well, just by intuition, if I have more samples, I'm going to do better or worse? Much better, right? So you expect that the variance to decrease with the sample size n? We know that it's biased, so we know on average. That is, what it means is on average. If you consider many, where did I write it here? Many sets of size n, and you calculate for each set this number, and then you average them, that would be the correct probability. Right? But you don't want the spread of this number to be very large. So this is why you need to do the variance. So we know the definition of it, right? So this is random variable. Minus its mean value, and we know the mean value, right? That's the definition of the variance. The random variables minus the mean value square, expectation. Right? And now we just have to do some calculations. So you want me to write them here, or you do them by yourself and discuss in the afternoon? How you prefer? We already passed the time, right? Come on, I need a vote here. It's democracy after all, right? You take like 3-4 minutes. Okay. So nobody's going to jump on me if I work. Okay, all right. So the first term square. Right. So I'm going to write it explicitly, 1 over n sum. Right, that is this formula. Critic, okay. So this is the first term square minus a minus b square, right? A square minus, this is what I'm doing, nothing sophisticated, guys. 2 expectation of the cross product, right? So PS and I can pull this out because it's a deterministic number. And plus the last term square. Right? These two terms is clear. This is PS square. Okay, right? And what else? We have that. What about this term here? What can I do about this? So this is taking some doing. How shall we proceed with it? Well, you have a sum square, right? So you have to multiply sum by sum. It turns out into double sum. Okay? And then we have to use the independence. So this I hesitated whether to do it right now or not. Okay? So I start you here, so let's finish it in the afternoon. But not, I mean, late in the afternoon when we do the application interaction, right? But please think about it and tell me maybe how to solve it. Because immediately when we start after lunch, I begin to talk of random functions. So I don't want to interfere with this part right now. Okay? All right, so we left this for later in the afternoon.
Okay, it was a nice review of all the basics so that you can go ahead after lunch. So thank you very much for this.